Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 48. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with effect of capacitive reactance in transmission line. Capacitive reactance would be the important factor so far the presence of harmonics in the system. It is as because that the capacitive reactance Xc is inversely proportional to the frequency of the harmonic present. Basically, the capacitors are of the linear reactive devices, so they do not have the characteristics to produce harmonics. A three-phase overhead high-voltage transmission line with phase conductors are symmetrically spaced so as to ensure proper insulation. The power carrying capacity of the transmission line and the voltage drop across it at full load would have been characterized by a series resistance, inductance, and shunt capacitance per unit length. That is, per unit length of the conductors. An alternating current, while flows through the conductors of the transmission line, then an alternating magnetic flux will be set up along the conductors. Since the current is thereby alternating in nature, hence the flux linkages with the conductor would have simultaneously be changed. Hence, performance of transmission line must have to depend on the parameters such as resistance, inductance, and capacitance, etc. Type of wire, which is mainly of standard transmission wire, whose material composition would have to comply different types of properties such as stability, strength, conductivity, etc. All these parameters are responsible for interrupting transfer of power through a transmission line. Resistance is the most critical property of the line conductors, that it causes power loss in a transmission line, that is I square R loss. Inductance is the property of capability of a conductor to oppose the change of flow of current through a particular circuit. According to the Faraday's laws of electromagnetic induction, the magnetic flux starts to produce when the current passes through the conductor. The generated flux that would have to vary with the variation of current, resulting in an induced EMF, electromotive force. This electromotive force that is induced during this process is because of inductance. This electromotive force that is induced during this process is because of inductance of the line. The transmission lines transmit high voltage and current which are alternating in nature. When the high alternating current is passing through the conductor, then high alternating magnetic flux would have to generate, which will thus to form a linkage with the other flux generated by the neighboring conductors parallel to it. Most important. Again, I repeat, when the high alternating current is passing through the conductor, then high alternating magnetic flux would have to generate, which will thus to form a linkage with the other flux generated by the neighboring conductors parallel to it. However, The inductance of a transmission line is given by the ratio of number of magnetic flux linkages to the current flowing through it. That is L equals to lambda by I, where L is the inductance, lambda is the number of flux linkages, that is Weber turns, I is the current. The total magnetic flux linkage can therefore be estimated by the two components. One, flux linkage to a conductor due to its own current, that is internal phenomenon. Number two, flux linkage due to current in the neighboring conductors, that is external phenomenon. So, flux linkages as exhibited would have been both internally and externally, and of a subsequent effect for series inductance of a transmission line are also to be characterized by two components, that is internal and external inductances. The inductance and capacitance of a power transmission line that would have to depend on several factors, including the diameter of the conductor, line length, spacing between the phase conductors, and the load current carried by the conductor. Number one, space between the phases, if it is made to increase, then there will be an obvious increase in inductance, and at the same time a decrease in capacitance value of the line. Number two, conductor of a large diameter has a lower inductance as the magnetic field produced by the current is spread over a larger area. Number three, larger be the diameter and longer be the length of the conductor, higher will be its capacitance. As because a conductor of larger surface area can store more charge than a smaller conductor. A longer transmission line has a higher inductance because the magnetic field generated by the current has a longer path to travel. These four is much more important. Whenever we are discussing the inductance and capacitance of a transmission line, then the term reactance has come as a quantity that opposes the change in current. Reactance that would cause a 90-degree phase shift between voltage and current, which is based on whether the component is just on inductor or a capacitor. So, the reactance is the term which has only to imply both on series and parallel composition of AC circuits and not to apply in the DC circuits. Inductive reactance XL and capacitive reactance XC are the two types of reactance. If a circuit contains both inductance and capacitance, then the generated reactance of the respective components would have to oppose each other. Hence, the circuit's total reactance X can be measured by the difference between the two, that is between XL and XC. When an alternating current passes through any electric circuit which contains reactance, where energy would have been stored to compute the change in phase and magnitude of the current and voltage waveforms. Again, I repeat, when an alternating current passes through any electric circuit which contains reactance, where energy would have been stored to compute the change in phase and magnitude of the current and voltage waveforms. The energy is thus to be released in the form of an electric field or magnetic field. Releasing energy in the form of magnetic field, the reactance would have to resist the change in current. And releasing energy in the form of electric field, the reactance would have to resist the change in voltage. The reactance, if it is being inductive, then it releases energy in the form of magnetic field. The reactance, if it is capacitive, then it releases energy in the form of an electric field. This is the difference. The reactance, if it is being inductive, then releases energy in the form of magnetic field. Whenever the reluctance, if it is capacitive, then it releases energy in the form of an electric field. It is therefore to be concluded that inductive reactance may have to resist the change in current configuration. B. Capacitive reactance may have to resist the change in voltage configuration. This is the difference. The inductive reactance XL can be expressed as where XL equals to twice pi FL ohm. F is the frequency of the alternating current measured in hertz. L is the inductance measured in Henry. The capacitive reactance XC can be expressed as XC equals to 1 by twice pi FC ohm. C is the capacitance measured in farads. With the increase in frequency, capacitive reactance is decreased and inductive reactance is increased. As of the Lenge's law, where it is clearly mentioned that the flow direction of the current produced as due to inductive reactance is opposite to the direction of the main current. The resultant effect would have to create a power lag between the waveforms of voltage and current. As of the expression, the inductive reactance is therefore directly proportional to the frequency of the current and the inductance. Whereas capacitive reactance is inversely proportional to the frequency of the applied voltage and the value of capacitance. The inductive reactance is therefore directly proportional to the frequency of the current and the inductance, whereas capacitive reactance is inversely proportional to the frequency of the applied voltage and the value of capacitance. Long transmission line is usually composed of significantly higher amount of capacitance and inductance distributed along its length. Long transmission line, while is at no load or highly loaded, the distributed capacitance of the line draws more current. The capacitor charging current as flows through the distributed inductance of transmission line would have to create a voltage drop it which is rather in phase with the sending end voltage. The capacitor, again I repeat, the capacitor charging current as flows through the distributed inductance of transmission line would have to create a voltage drop across it, which is rather in phase with the sending end voltage. As of its consequential effect, the receiving end voltage would have become greater than the sending end voltage. That is Ferranti effect. This overvoltage phenomenon in the receiving end is known as the Ferranti effect. The Ferranti effect is caused mainly because of the capacitance of the transmission line, which generates a reactive current that flows through the line, which can create a voltage rise at the receiving end. Therefore, such phenomenon would have the effect to generate the reactive power, which is more than the reactive power as absorbed. To get rid of this effect of voltage rise, it is thus to be essential to compensate the reactive power as generated in transmission line. The best possible solution is to install an additional shunt reactor at the receiving end and long end of long high voltage transmission lines. A shunt reactor is mainly an inductive coil, which would thus to act as a reactive power absorber to enhance the energy efficiency of the system. Shunt reactors, mostly of oil immersed types, are being suitably designed to install at high voltage and extra high voltage system and can have to be directly connected to the power line or to a tertiary winding of a 3-winding transformer. However, reactors, if connected to tertiary winding of 3-winding transformers, there will be of the lowest cost but must have extra losses which would have been obtained in the transformer. However, reactors, if connected to a tertiary winding of 3-winding transformers, there will be of the lowest cost but must have extra losses which would have been obtained in the transformer itself. See the diagram. Power generation, generating unit, line impedance, shunt reactor connected to the tertiary winding of the transformer or directly connected to the system, shunt reactor, load. One filter circuit is there, RC snubber filter. While designing the rated voltage of the reactor as well as the extent of voltage drop at the power transformers must have to be taken into consideration. While designing the rated voltage of the reactor as well as the extent of voltage drop at the power transformers must have to be taken into considerations. Based on the voltage requirement, shunt reactors are thus to be switched on or off to provide reactive power compensation. Dedicated relay is therefore to be integrated at the circuit so as to have a perfect synchronization of switched on or off of the respective circuit breaker of the connected shunt reactor. The relay that would have to actuate and send the closing impulse at the correct instance to achieve pole closing of the shunt reactor circuit breaker at maximum phase voltages. Variable shunt reactors are then to be developed, which allows to accommodate frequent variation of load in transmission network with having a provision of continuous adjustment of the reactive power compensation activity. Points to be noted. 1. System voltages up to 400 kV. The shunt reactors are usually of three-phase type. System voltages up to 400 kV, the shunt reactors are usually of three-phase type. Whereas, number 2, for voltages above 400 kV, it is rather recommended for single-phase type shunt reactors. When the total line reactance of a power network becomes high, then a connection of series capacitors that would have been very much effective to neutralize a part of the inductive reactance. This has resulted an enhancement of the load voltage, and as of the subsequent effect, there is not only improved the stability of the system network but also increase the circuit's transmission capacity. Number 5, the series compensation by installing series capacitors is an economic method of improving power transmission capability of the long high voltage, extra high voltage and ultra high voltage lines. Installation of series capacitors in long transmission lines will have the effect on system performance as stated. 1. Directly compensating the inductive reactance of the line network. Directly compensating the inductive reactance of the line network. Number 2, as the series capacitors are responsible to offset some of the line reactance, so there must have a greater thermal capability of the line, which ultimately would have to enhance the power transmission capability. Number 3, improvement in system stability. Number 4, significant reduction of system losses. Number 5, improvement in voltage profile of the lines. Number 6, series capacitors can even be considered as a voltage regulator, which is only to provide for a voltage boost, and that is to be proportional to the magnitude and power factor of the through current. Number 7, better optimization of power flow sharing between parallel lines. Relation between harmonics and capacitive reactance. In an AC circuit, the capacitive reactance can be referred as the opposition that is to be offered from a capacitor to the alternating current supply. Actually, the presence of capacitive reactance in capacitor that intends to resist the changes within the potential difference across its two plates. That is, capacitors are configured with two plates. So, actually, the presence of capacitive reactance in capacitor that intends to resist the changes within the potential difference across its two plates. The capacitive reactance is inversely proportional to the related source frequency and capacitance, figure 160. As stated earlier, capacitors that would have been highly sensitive to the presence of harmonics due to the fact that the capacitive reactance Xc is inversely proportional to the frequency of the harmonics exist in the system and the value of the capacitance. See the diagram. Reactance in ohms, frequency. The reactance of capacitors would have been decreased proportionately to the frequency of the harmonics present. The reactance of capacitors would have been decreased proportionately to the frequency of the harmonics. It is as of the figure. Capacitive reactance can be represented by the impedance of that capacitor. Capacitive reactance can be represented by the impedance of that capacitor. As the impedance of the capacitor would have to decrease with increase in frequency, so large harmonic current that has to flow through the capacitor. The elevated current that may lead to certain possibility of overheating the capacitor with the degradation of its dielectric, which may result in its eventual failure. Dielectric of the capacitor itself. However, as the order of the harmonics frequency increases, the inductive reactance increases while the capacitive reactance decreases. Situation would have become much worse if somehow harmonic resonance starts occurring. Harmonic resonance is a phenomenon which can occur in a power system while at a particular frequency of harmonics, the inductive reactance and the capacitive reactance of the power system would have become equal. Harmonic resonance can cause major system instability due to transient high or low voltages. Harmonic resonance can cause major system instability due to transient high or low voltages, and sometimes may have damaged electrical components such as failure of transformer windings or failure of capacitor. Capacitors are widely implemented in the electrical system network for power factor correction. However, the working of capacitor banks under a harmonic rich environment may be adversely affected. The resonance between the inductance of the transformer and the capacitance of the capacitor banks may sometimes happen at specific harmonic frequencies, though the capacitor would not generate harmonics, but the capacitor can magnify the harmonic current under resonance condition. Most important. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the comments and feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.